Good morning, ladies and gentlemen. Welcome to Yokogawa's Analytical Web Seminar, The Vibrating Element Technology, the Measurement of Gas Density, Specific Gravity, and Hydrogen Purity. We would like to thank you all for taking the time to attend, and we hope you find this seminar helpful and informative. Before we begin, we would like to go over some housekeeping issues. The audio part of the seminar can be accessed either through the teleconference number provided in the Info tab of your WebEx Manager window or through your PC speakers. To hear the audio through your PC, select the Communicate tab and join the audio broadcast. The seminar will last approximately 1 hour. Towards the end of presentation, where time permitting, we will have a question and answer section where our featured speaker today will answer some of the questions received from the audience. If your question is not answered during the presentation, please be assured that we will answer them directly via email or telephone. All questions should be submitted in either the question and answer window or the chat window located in the lower right-hand corner of your screen. Today, our featured speaker is Dale Cathy. Dale is the Analytical Gas Product Manager for Yokogawa. He has worked for Yokogawa for over 10 years. Prior to joining Yokogawa, he earned a degree in microbiology from Louisiana State University and worked in laboratories for the refining and chemical industry for 5 years. We would like to get the seminar started by handing it over to our featured speaker, Dale Cathy.
Good morning, and I want to thank you for attending this introduction to vibrating element technology. We're going to discuss how this technology works and where you may find it useful in your facility. We're also going to briefly touch on the other technologies that are used to make this measurement so we can compare and contrast the two. The presentation should only take about 30 minutes, so we should have plenty of time for a question and answer session afterwards. So please feel free to type in your questions as we move along. Now, the primary measurement of the vibrating element analyzer is gas density, and it's from this primary density value that we are able to calculate a number of secondary values. In any application, basically with any combination of gases, we are able to calculate specific gravity and molecular weight from the density. In certain applications, specifically binary gas streams or pseudo-binary gas streams, we can also calculate a caloric value, or BTU, or an actual percent concentration of a constituent of the gas stream. We will discuss later a specific example of percent concentration applications, which is hydrogen purity in a power generator. Now, these are the components of a basic vibrating element system. Starting at the bottom, we have a detector where the actual vibrating element resides and where the gas that is being measured is connected. Also connected to the sample gas is a pressure transmitter that is used for real-time compensation. Now, these elements are all connected via cables to the analyzer, and it's the analyzer which receives the inputs, calculates, and then transmits the values via 4 to 20 milliamp signals. Now we'll discuss the primary measurement of the vibrating element, which is what we had said earlier is gas density. And here we have a very basic illustration of the vibrating element detector. It's comprised of a cylinder, which is the resonator, within another cylinder, and all of this is inside a protective cover. Now the gas being measured is introduced and flows between the two cylinders, and a piezoelectric actuator forces the resonator to vibrate. And the resonant frequency at which the cylinder vibrates is going to be dependent on the density of the gas that is surrounding it. Now, this frequency is measured by the detector and transmitted to the analyzer, which then calculates the gas density based upon that frequency. Now, you'll also notice a temperature sensor within the gas stream that is also used for real-time compensation. Now, some vibrating elements utilize what we call a multi-mode oscillation. In these systems, the cylinder is forced to vibrate in 2 different modes, an axial mode and a circumferential mode. Now, this, of course, results in 2 different frequencies that are measured, and the density is then calculated not by the magnitude of the frequencies, but by their ratio. Now, as the gas density increases or decreases, this ratio between the 2 frequencies will also increase or decrease. Now, this illustrates the advantage of using a vibrating element system with multimode oscillation. Now, the magnitude of the resonant frequency is not only affected by the gas density, but also by the accumulation of dust, oil, or other contaminants. Now, if a system only measures the magnitude of a single frequency, this will create a measurement error as contaminants accumulate. In a multi-mode oscillation system, the accumulation of contaminants will affect both frequencies equally, leaving the ratio largely unchanged. This makes a multi-mode system much more resilient in these harsh applications that may contain a number of contaminants. Now, most vibrating element detectors have an integral temperature sensor which measures the temperature of the gas sample itself. Now, this allows the system to measure the raw density of the gas at process temperature, but it also allows us to calculate a density value at a standard reference temperature. This is typically 0 degrees Celsius. Now, this also means that neither the gas sample nor the detector itself has to reside in a temperature-controlled environment. What the illustration shows here is a test where a vibrating element detector is placed in a climate-controlled chamber and is exposed to temperatures that are ramped up and down, and you can see that there's very little effect on the density measurement itself. Now, also earlier we noted that some vibrating element systems feature a pressure transmitter to monitor the pressure of the sample gas. Now, once again, this allows the calculation of a raw density value at process pressure, but it'll also allow the instrument to calculate a compensated density value at a standard reference pressure. Typically, this is at 1 atmosphere of pressure. Now, this also allows the sample gas to be introduced at a fairly large range of process pressure, and this reduces the amount of sample conditioning that's required before the gas is introduced to the instrument. Now, this illustration shows a gas stream whose constituents, its stream components, remain the same, but the pressure of the process is gradually decreased. Now, this results in a decrease of raw density at process condition, but the analyzer calculates the compensated density, which remains unchanged. Now, the correlation between the output of a vibrating element system versus gas density is very linear in nature. This allows the instrument to cover a very wide range of density values based upon a single calibration. The analyzer is capable of accurately interpolating and extrapolating density values within and beyond the scope of the calibration gases used. And what this allows us to do is to use very safe and inexpensive calibration gases that are readily available. Now we're going to discuss how the system can calculate a percent concentration based on gas density. We're going to talk specifically about a power plant application, and it's where the purity of hydrogen gas used to cool generators is measured. First, a little background on why hydrogen is used to cool power generators. Hydrogen is very efficient at conducting heat, which means it'll readily absorb heat from the equipment that is to be cooled. Hydrogen has a very low viscosity compared to other gases, and that low viscosity means less friction or windage will be created by the rotating equipment, and this allows the electricity to be generated more efficiently. Also, hydrogen is one of the most abundant substances on Earth, which translates to relatively low procurement costs. And the purity of the hydrogen is measured for two main reasons. One is safety, and the other would be efficiency. The explosive range of hydrogen in air is 4 to 75%, so the hydrogen concentration must be kept outside of that explosive range. And also, the higher the hydrogen purity, the more efficiently electricity is generated. In this next slide, we'll see an illustration of that. As the hydrogen purity decreases, you see that thousands of dollars are lost due to the decrease in efficiency. This is because that rotational energy is being transformed into a heat energy friction rather than electrical energy. And you can also see that this effect is multiplied as the capacity of the generator increases. Now, the three gases involved in generator applications, there's three of them, each of them with their own distinctive density. Hydrogen, which flows to the generator to cool in normal operation. During that normal operation, air is in a contaminant due to leakage. Also, there's carbon dioxide, which is used to purge the generator of hydrogen when the generator is shut down for maintenance activities. Now, once the generator is purged of hydrogen, the carbon dioxide is then purged out with air, so the environment is safe for technicians. Now, this is considered a binary gas application because only two gases are of concern at any one time. We would be concerned about hydrogen in air during normal operation, hydrogen in carbon dioxide during the first purge cycle, and air in carbon dioxide during the second purge cycle. Now, by measuring density in a binary gas stream, we can calculate percent concentration based on a simple calculation. So we have known values for the constants, and these are the zero and span concentrations and their associated densities. The only variable is the actual density of the gas, which is dependent on the concentrations of the two gases in the process stream. Now, as an example, if we want to measure the purity of hydrogen in the range of 85 to 100% in air, we know the densities associated with the span and zero concentrations. We simply program these constants into the analyzer. The analyzer measures the density of the process stream, and based on that density, it calculates the percent concentration of hydrogen. Now, this illustrates what the output of a vibrating element system typically looks like in these types of applications. 1 4 to 20 milliamp output represents the percent concentration of hydrogen in air. The second output represents the concentration of hydrogen in carbon dioxide or the concentration of air in carbon dioxide, depending on which purge cycle is being performed. Now, this setup allows one vibrating element system to act as a tri-gas analyzer, where all three situations can be monitored by one system. And here's a typical installation or configuration for these applications. The sample from the generator is brought in through a system of valves, and they're configured to allow the selection of calibration gases. The sample is then passed through a coalescing filter to drop out moisture and a pressure regulator to knock the pressure to below 70 psi. A needle valve and a rotometer are used to control the flow of the gas between 0.1 and 1 liter per minute. From there, it flows through the detector, its pressure is measured, and then it can be exhausted to a vent line or back to the generator. Now, calibrations for these applications are performed with two gases, 100% hydrogen and 100% carbon dioxide. And we choose those two because they bracket the full range of densities that the analyzer will measure. Since we are calibrating the density measurement, the very light hydrogen gas is actually the zero calibration gas, and the much heavier carbon dioxide is used as a span calibration gas. And it is recommended for these calibrations that you use instrument or calibration grade gases, not bulk gases. That way we'll ensure the most accurate density measurement possible. Now, in a perfect world, the detector we know would only see a clean and dry sample, but we know in the real world this isn't the case. These samples can often be contaminated with seal oil, sometimes to the point where the detector is completely flooded with the oil itself. Now, vibrating element detectors can be salvaged from such an event on site. The detector can be easily cleaned with a detergent-based solution, rinsed with water, then rinsed with pure isopropyl alcohol, and then the detector can be dried with instrument air, calibrated, and then placed back in the service. Typically, there's no need to send the unit back to the factory for repair. Next, we're going to discuss some applications for the vibrating element system found in refineries. These are typically specific gravity applications, but in some cases, hydrogen purity can be calculated. The applications where hydrogen purity can be calculated are typically multi-component streams that act as a pseudo-binary gas stream. In these cases, the hydrogen concentration, as it increases or decreases, the concentration of the other components increase or decrease at the same rate. And that means the density of the background gas can be calculated and treated as a second gas in a binary system. Now, the first refinery application we're going to discuss are hydrotreators, which are found throughout the refining process. Now, hydrotreaters or hydrodesulfuration units remove sulfur from products of distillation like naphtha, diesel, or gas oils. And the sweetening process protects the catalyst used in downstream units, specifically reformers, and reduces sulfur dioxide emissions when the final product is burned. Now, a little bit of background on the process of hydrotreaters. The feed is going to be mixed with hydrogen, heated up to 300 to 400 degrees Celsius, and then pressurized. This mixture is sent to a reactor containing a fixed bed of catalyst, which is typically alumina-based and impregnated with cobalt. Now, the simplified layout shows the hydrotreating process and points where specific gravity or hydrogen purity can be measured. improve the efficiency of the process and to reduce the hydrogen consumption. The gas coming off the separator can be measured to indicate hydrogen content. This will determine how much makeup hydrogen is required to increase the hydrogen concentration to a required level to recycle it back to the process. And the makeup hydrogen can be monitored as well to confirm its purity. Now, another application in refinery is the catalytic reforming of naphtha. Catalytic reformers convert the sweetened naphtha that just went through the hydrotreater, and that naphtha has a low octane rating, and the reformer will convert that into a high octane rating reformate. And this is done by reforming the straight chain feed molecules into a branched or cyclic molecule. Once again, this feedstock is mixed with hydrogen, then pressurized and heated, and it's sent to a series of reactors containing the catalyst. These are typically platinum. These are the catalysts that we were trying to protect from the sulfur components before with the hydrotreating. The products of this process is a high-octane reformate liquid and a hydrogen-rich gas, which is due to the dehydrogenation of straight-chain molecules. Now, once again, on this layout, you can see that the gas coming off the separator can be measured to indicate its hydrogen content. This can be used to determine if the gas needs to be enriched with makeup hydrogen, whether it's recycled back to the reformer process, or whether it's sent to other units such as hydrotreators, or any combination of these scenarios. Now, hydrocracking is another refining application that may benefit from vibrating element analyzers. Hydrocrackers break heavy, long-chain gas oil molecules into shorter, lighter, more valuable molecules. Carbon bonds are broken, followed by hydrogen saturation. Typical feedstock is going to be coker gas oil and gas oils from the distillation process. And this should look pretty familiar. The feedstock is mixed with hydrogen and pressurized and heated. This mixture is sent to your reactor containing a catalyst, once again, typically platinum, where the actual cracking takes place. The hydrogen-rich gas is then separated from the cracked product, which is then sent for further distillation. And once again, you can see that the mixed hydrogen-rich gas coming off the separator is measured to determine how much makeup hydrogen is required to recycle that gas back to the process. And the purity of the makeup hydrogen can be measured as well. When we're doing calibrations for these density or specific gravity applications, we simply want to choose calibration gases that bracket your normal measuring density. A 2-point calibration, a 0 and a span, is preferred. However, if the density of the process does not vary widely, it is acceptable to choose a single-point calibration. You want the calibration gas there to have a density very close to your process density. And once again, the linearity of the measurement allows for safe and inexpensive off-the-shelf calibration gases. For example, if the density of your process has a density that's very close to, say, acetylene, most people don't want to have acetylene sitting around for calibration. It's flammable, it's dangerous, so you can choose something that's, has a close density to that value, but it's much safer, something like nitrogen, something like helium. Now, the last application we want to discuss is calculating the BTU content of a binary gas stream. Many facilities will have a backup propane supply system for times when their normal natural gas supply is unavailable, or in times of high natural gas prices, it may be more economically advantageous to consume propane rather than natural gas. But since propane has a higher BTU value than natural gas, it must be diluted with air if they want to utilize the same burner settings as those used with their normal natural gas supply. So as with percent concentration calculations, we can use a simple calculation to calculate the BTU content of the binary gas stream based solely on the density measurement. We know the densities and the BTU contents of the 0 and span ranges of the binary gas stream, so we simply just program these constants into the analyzer. The analyzer will then calculate the BTU content based on the measured density. Now, these are just a portion of the applications that can benefit from vibrating element systems. Other applications include measuring the density of fuel gas to correct orifice-type flow meters, Also, specific gravity can be used in compressor control schemes to prevent slugs of light gases from damaging expensive equipment. So now what we want to do is briefly discuss other methods available to make these measurements so that you're able to compare and contrast them with the vibrating element technology. One method to measure specific gravity is the fan differential analyzer. It's also known as a kinetic energy or viscous drag type, or by its well-known brand name. This analyzer has two chambers, an air chamber used as a reference and a sample chamber for the measured gas. Each chamber has a motor-driven impeller which draws the appropriate gas into it. Each gas will then come in contact with the stationary impulse wheels and is then vented out of the analyzer. Now, the impulse wheels are linked to each other, and the torques created on the wheels by the flow of the gases are directed in opposite directions. The magnitude of the torque is going to be dependent on the specific gravity of the gas. Now, this is a purely mechanical means to determine if that sample gas is lighter or heavier than the reference air. And one thing you may notice about this method is that it does have many moving parts that are going to be subject to wear. There are motors, impellers, impulse wheels, and linkages. Now, this will require calibration to compensate for this wear, or a drifting measurement will occur. Now, this method also consumes reference air that needs to be the same pressure and humidity level of the gas being measured. And it also does not take a whole lot of imagination to understand how a dirty sample containing particulates or oil affect the accuracy of this method. Thermal conductivity is another method employed to measure percent concentration in binary gas streams. Each gas has the ability to conduct heat at a specific rate, so this is known as the thermal conductivity of the gas. In thermal conductivity analyzers, heated metal filaments or thermistors are exposed to reference and sample gases. The amount of heat carried away by the gases changes the temperature of the filaments, which also changes their resistance. And since the filaments are arranged in a Wheatstone bridge, the resistance can be converted to an electrical current. And the magnitude of this current is going to be dependent on the thermal conductivity of the two gases. And that way, the concentration of the sample gas is calculated based on the thermal conductivity value. Some things to consider about this method. One is that a reference gas is required. Also, the detector must be kept at a stable temperature through the use of heaters or ovens. These ovens also require warm-up time to reach these target temperatures. Now, it's also recommended that the flow rate of the sample gas be held constant to prevent cooling of the filaments due to increased flow rate versus actual changes in thermal conductivity. And also, since thermal conductivity versus the concentration of increasingly heavier hydrocarbons, it's not a linear relationship, so multi-point calibrations with blended gases may be necessary in certain applications. And lastly, it would be fairly difficult and rather expensive to restore this type of analyzer to working order in the field if it is significantly contaminated with oil. Just a brief summary about the vibrating element technology. It's proven itself in the field to be a reliable, stable, and accurate measurement. It is linear over a very wide range. It does not require a isothermal condition, so there are no ovens or heaters, no warm-up time associated with it. No reference gas is required. Calibration can be performed in just a few minutes, and that's in just a few minutes after the instrument is turned on, since there's no warm-up time. We're able to use standard calibration gases. We don't have to fool with custom blended specialty gases that may be fairly expensive. Due to multi-mode oscillation, the analyzer withstands dust and oil in the sample gas fairly well, which allows it to be virtually maintenance-free. And in a bad situation where the detector itself is slugged with large amounts of oil or contaminants, it is easily cleaned on site and able to be put back in service without having to send the unit back to the factory for repair. And also, it's a tri-gas analyzer, which means for those power plant applications, it's only one unit required to measure hydrogen, air, or CO2.
Great. Thank you, Dale, for a wonderful presentation. Once again, we'd like to thank you all for attending and participating in this online web seminar. It was only about 30 minutes, so we have some time allotted for some questions and answers. Feel free to type them, again, in either the chat window or the Q&A section on your lower right-hand corner. And if you have no questions, we would just like to mention that the seminar was recorded and it will be available again for replaying 24 to 48 hours underneath our technical library of our web page. And we would hope to see you online in some future web seminars. Yeah,
vibration, assuming process vibration. The frequencies at which we cause this resonator to vibrate at are very high. Typically, they're not going to be in the range of anything we'll see as far as vibrations induced from process equipment, such as pumps or compressors or anything like that. So, we do have test data that shows that the instrument itself is fairly immune to vibration caused by process equipment itself.
Alrighty, once again, we would like to thank you, ladies and gentlemen, for joining us. Some of the questions that have come through are they're not within the scope of the presentation. Once again, we will answer you directly via phone call or email. So thank you, ladies and gentlemen, for joining us, and keep your eye out for some more online seminars. Thanks, and have a great day.